everyone for this week's Machine Learning Coffee Seminar. This week we have a really exciting talk by Timo Koski on Jensen-Shannon divergences. If you have any questions during the talk, please write them in the chat, so then I will direct them to the speaker. Okay, so Timo, please go ahead.
Thank you. Thank you. Okay, today I'm going to tell you about an approach to likelihood-free inference that is somehow a bit different than the what you have. Oh, no. Yes, well, and anyway, this is or actually the story is initiated by Jukka Kurander, who you probably know, and some of you at least here in Helsinki, and then by Ulpu Remes in Oslo. Jukka and Ulpu, they are working at the Department of Biostatistics in the medical faculty of University in Oslo. Funding, you see the grant numbers, but I have been supported by the Finnish Center of Artificial Intelligence for my visiting here, for which I'm very grateful for. Now, let me get into my topic here. I'm restricting myself to categorical data, and I'm going to use this calligraphic A for a discrete alphabet that has K categories. K is known, and here's an example of a categoric alphabet. Now they are the sizes of T-shirts, and now in this case there is also an order. I mean, XS is smaller than S and so on. Order doesn't really matter much to me in this talk. I'm not going to be talking about ordering things. There's an application where this theory has been applied just in terms of algorithm by Jukka Kurander in his studies of antibiotic resistance of bacteria. There's a very complicated description of the categories, which I'm not going to start reading out loud. Now, so this has been applied, but we are doing the theory, an analysis of and proving that it's correct in a sense. I'll give you the reference later. So now I have this capital D that denotes a set of observations. So they are n sub 0 of them. Now the sub 0 may look, it's for n observations, and it's simply somebody has generated to me a sample of data with values in this alphabet. Now there was this likelihood-free inference thing, and now I'm going to start by simply giving you some paraphrases of what's in this paper. So now, as in the paper, we are talking about the MC, a computer program, and that's a simulator model for the data source. I mean, the data source that generated with the data D. And then when you put an input to the program with a random number, I mean simulator, and then a parameter, then you get a random variable X that has values in this alphabet. So you would. So it simply is a way of so the point is that this as has been this MC can be extremely complex and sophisticated. So you're not restricted to having models that are sort of that you have to simplify in order to make them analytically or computationally tractable. And this likelihood-free inference is now a way of using the simulations and the data together with the simulator model to make inference. I'll try to explain that. So now here are the sources. This paper number 2 is what I was already referring to, but we are now and the question here is now to use this D and the simulator model to make inferences about theta. And the abstract of my talk is the following, that we show that there's a method called Boltz. I don't know how to pronounce it, but anyway, you see how it has been, how it is generated from the first letters of in the Bayesian optimization for likelihood-free inference. And this is a method with kind of that does the learning and inferences. And what we are going to do is that we use Boltz, however, with the discrepancy function that's specialized, that has been introduced or has been used in this tool. And then we'll show that this thing here is equivalent to an implicit maximum likelihood estimate. Now, I haven't defined implicit likelihood. I haven't defined discrepancy or divergence, but that's part of my talk here. Now I will start by looking at the defining implicit models and the situation likelihood-free inference, and then I'll give the discrepancy, which is the Jensen-Shannon divergence, and connect that to LFI likelihood-free inference. And then there's this result part where I'm giving the statistical asymptotics of the Boltz and then simulation experiment. And if time permits, I'll say something about this divergence. Okay. Usually this LFI has two ways of doing this. They try to find an explicit surrogate likelihood, or they use this ABC. They simulate, and then there's some sort of acceptance of parameter values or rejection of parameter values. Now, this work is somehow taking features of the both of the above. It's neither of them in a clear-cut way. So now here comes some notation. Namely, here the point is that now if I run my simulator model with the parameter theta, then that induces a probability. If the probability is on this alphabet in this way. Now, of course, now here's a bit of notation, which is sort of self-explanatory. What happens is that there's a categorical distribution on probability distribution on the alphabet induced by the simulator model, and I write it in this manner. I mean, this is I think it's a nice way of writing it, because it sort of like is a real distribution with argument in the alphabets. And it's simple. I mean, if the x is a1, then all the rest here are 0, and you get p1, which is actually the meaning here. But it's a notation used in. So because this is a complex thing. This model, you cannot write down this. I mean, you know it is there, but you cannot write it down explicitly, and therefore the likelihood inference is likelihood free, because you have to find some way of replacing and approximating the likelihood function. Now there is an old paper by an old 1984 paper that uses the word implicit statistical model in a situation like this. So you could say that the simulator model it's represented by a statistical model of this kind, which is, however, is implicit since we don't have the likelihood function. And here yes. Right. So this is they use the terminology of prescribed categorical probability, where you could have like your probability distribution explicit. Now here's an example. I only have this example because I will need this particular symbol later on, and there's the name of the paper on implicit statistical models. Now the discrepancy is between the observed data and the simulated data, and and you need to approximate the implicit likelihood, and the approximation is done by looking at implicit the summary statistics. And in this work, the summary statistics are the empirical distributions p hat d and p hat x theta that are based on our data. Now, and then the discrepancy will be with this Jensen-Shannon divergence between these two empirical distributions, p hat d and p hat x theta. Now, in this ABC literature, there is a question about the when are you justified to summarize your data in some way. And here's a result: Bayes sufficiency, namely the summary statistics, the frequency, the empirical distribution is in fact Bayes sufficient. Namely, if you have to calculate the posterior distribution of the parameter given the data, it is exactly the same as the posterior distribution given the empirical distribution. This doesn't look, that's for any prior density on the parameter space. I don't know if I haven't seen this anywhere, so I claim that we have proved it, but maybe this is known already somewhere, but I haven't seen it anywhere for in this particular case. So now I'm going to introduce this Jensen-Shannon divergence, and quite generally, I'm here looking at two categorical distributions with different category probabilities pi and qi, and then I have to first define the Kullback-Leibler divergence, which is in some sense it's the expectation with respect to p of the likelihood ratio between p and q. Now, if the mathematical definition is here, if I use this Iverson notion, it turns out that in terms of these categorical probabilities, the Kullback-Leibler distribution looks like that, very well known, and you have seen it probably, very familiar. Now, this Kullback-Leibler distribution has very nice properties, and it has been used often, and it's non-negative, which is of course, and it's zero if and only if p and q are equal to each other. It's not symmetric, and it's possible that this Kullback-Leibler is unbounded. It can be plus infinity in a situation where p and q are not absolutely continuous with respect to use mathematical jargon here. And it's not a metric, although statistical learning literature deals with it as it were a metric. Now I'm defining Jensen-Shannon divergence, and Jensen-Shannon divergence. Okay, I have the p and q from preceding slide, but then I introduce an m, which in terms of these coordinate probabilities it's a sort of like convex mix of p and q, and then I define, this is my definition of Jensen-Shannon divergence. It is that I calculate the Kullback-Leibler distances or divergences between p and m and q and m, and then I make the same convex combination of these two Kullback-Leibler divergences. And if I use this Iverson symbol, I can write it down in terms of the categorical probabilities like this. Now, there are names of people that have been working on this. Actually, now both Kullback-Leibler distance and a divergence and Jensen-Shannon divergence are special cases of what's known as phi divergences or Chisar's phi divergences. So you can study, if you study phi divergences, you get results here. They are valid for Kullback-Leibler as well as for Jensen-Shannon. And by one of these results, there is this range of Jensen-Shannon divergence. Namely, it is non-negative. If it's zero, then p and q are equal to each other. But there's an upper bound given by the binary entropy function like that. And if I use pi equal to 1/2, then the range is maximal. I mean, this is the value of the binary entropy function in natural logarithm when pi is 1/2. When pi is 1/2, then it's symmetric, and it's a smoothing. So it's a smoothing of Kullback-Leibler divergence, because we don't end up in a situation where this can be plus infinity. So that's an advantage for all kinds of computations and algorithms with this thing here. It's not a metric. Now, Jukka Kurander uses only this case 1/2. And actually, if you take the square root of JSD with pi 1/2, then that is a metric. That's interesting. Also there's this Kullback-Leibler Jensen-Shannon divergence used in this GAN, generative adversarial nets. And there they usually have this pi equal to 1/2, at least what I've seen. I'm not an expert on this GNA. So now here is the empirical distribution. You simply P hat D. What you simply do is you calculate the number of times you see the symbol AI in the samples, and then you divide it by the total number of observations. Well, obviously, it's the same thing about this P hat XA, which is calculated from the simulator data. So now this Boltz is a technique or method for sort of optimizing this thing as a function of theta. The point is that this GJS it's not a contrast function or anything. You cannot. There's no way of inserting theta in a formula there. It's theta. It's symbolic because it corresponds to the value of theta used in the simulator model. But somehow this is able to. This is the Boltz, the computer software. You see there. There's a reference to its homepage and the documents, and it can optimize this by some clever techniques of proposing parameter values to run with, and this is implemented in what's known as ELFI. It's a software package, statistical one. I think it's from the Aalto University mainly in these days. And as I said, this is non-parametric. So now here is sort of like here's one result. We have, if you now fixed your observation number is fixed. I mean, it could be, it may not be easy to add to this. I mean, if you look at these bacteria applications by Jukka and his co-workers, it costs enormous amounts of money to get these the strains there. I mean, it's a $1 million business, million kroner or what Norwegian kroner business to have it. So you cannot, but you can simulate. You can easily simulate. N goes to infinity, and then it turns out that there's a consistency property here, namely this thing here, where it converges to the Jensen-Shannon divergence between the observed empirical data and the implicit probability distribution induced by the simulator model, and this is with simulator probability 1. Now this puts the matter into a different scape, because this is, of course, and here's another one which is a bit different. Namely, you can prove a sort of uniform convergence in with respect to theta if theta is in a compact subset of RD. Now D, the dimension of the parameter space, has to be smaller than the number of categories, and then you get this kind of uniform bound on the deviation of the Boltz statistic from its limit. So hence, I mean, mathematically speaking, we can turn our attention to minimizing this. This is what Boltz actually does asymptotically, or it minimizes this kind of thing. Now this is implicit again. Of course, we don't have it. So, but in mathematical sense, we are now dealing with actually minimizing it. Now this here thing is a special case of what's known as the minimum divergence estimates. And there's a rather nice paper about it by Morales, Pardo, and Vaida again, that studies the asymptotics of general minimum divergence estimates that also include the Jensen-Shannon divergence. However, they are interested in their analysis is explicit modeling. In addition, they are interested in goodness of fit. I mean, they try to get limiting distributions of chi-squared type. Now they don't have it, but we just to be sure of it, we prove that it actually the minimum exists for Jensen-Shannon divergence. I mean, it's again under the assumption of compact parameter space, and then we have to assume identifiability. There are no two thetas that could be different theta that could be the same simulator probability. And then I can show that there is a measurable function that actually exists, a measurable function that actually is the minimum Jensen-Shannon divergence. This is what we are saying here. Okay, that's just for, and then we get then we are approaching the main. This may be the main result, namely, if I assume that I have now I have to make one nasty assumption, namely I assume that actually our simulator model there is a parameter theta 0 such that our data could be simulated by the model. This is the true distribution assumption. I hate to say this, but I'm speaking here at the HIIT offices, and same office, and Jorma Rissanen spent a lot of time telling to everybody that this true distribution assumption is nonsense. But I need it mathematically. I'm sorry, the late Jorma Rissanen. So if I assume that this is and that my simulated distributions are positive for all category values, and if I even assume that my empirical distributions will always be positive for every category, then I can prove that the Jensen-Shannon divergence between the probability induced by the Jensen-Shannon minimum estimate and the maximum likelihood estimate goes to 0 with regard to the true probability distribution. And so in this sense, we now Boltz estimates this thing here. And if I got lots of data, these observations asymptotically, it actually calculates the implicit maximum likelihood estimate. So that's the result, and that's what we have been aiming at here. Now, to prove this, I won't go through it. I won't have time, and I don't think that you would be that interested. But I need the consistency properties, some of the Jensen-Shannon estimate, and then I need to bound these Jensen-Shannon divergences by this total variation distance. And to do this bounding, I need these all kinds of bounds from information theory, mainly the so-called reverse Pinsker inequality, and then a kind of symmetrization with the Jeffreys divergence. And then I need to know the fact that this thing happens here, namely, if there's a lot of observations, then the total variation distance between observed data and the true distribution is 0, which is not that surprising. So that's what the proof requires, and that's what to do. Now, yes, proof may be good, but you are probably more convinced if you can take a look at the simulation here. So here I have my alphabet is the k first positive integers, and I have a kind of geometric distribution on this alphabet. And this here the normalization constant is easily calculated by a geometric sum, so there's no problem there. So this is likelihood is neither implicit nor analytically intractable. The likelihood function can be written down explicitly, and if you differentiate this logarithm like log likelihood function with respect to theta and put the derivative equal to 0, then you see that the maximum likelihood estimate satisfies this equation, which is rather well known in theory of exponential families. And now we get the simulation. So what we'll do is that we create observation sets, I mean the observed data, using various values of k and theta, and then we use 50 observations. I mean, these are sort of simulation of the real data, 100, 500, and 1,000 data points each. And then for each of these observation sets, we calculate the maximum likelihood estimate and the minimum Jensen-Shannon divergence estimate. So here we have, and then yes, right. And then we also check different pi's, and this is not really so important, but so here is the case. Here is the case where pi is 0.4, and now here is now this n here in the figure should be no, like here. And now what you see here is that if I start with 50, then there's quite a lot of, these are the simulated values. There's quite a lot of sort of dispersion, maybe more in Jensen-Shannon. But when I get higher values, both of these are concentrated rather well around the true value, which was in this case was 0.5 and k was 5. And the same thing happens here with when pi is 1/2. You can see that maybe okay. Here the maximum likelihood and JSD estimate look pretty much the same. And then here is pi 0. Wait a minute, what happened now? The first one was 0.6. Sorry, maybe I jumped to. Anyway, now comes right. Okay. Now comes the interesting thing. Here we have this is the true value is 0.5, but the number of categories is 10. So you remember it's an exponential function; it decreases rather fast. And now you see here that with k here, this Jensen-Shannon divergence it overshoots rather heavily, even more than the maximum life. It sort of there's a bias upwards in this, which however keeps on disappearing when the number of observed data decreases. And this is something that's important here, namely now we increase the number of categories, and the probability of category 10 is rather small. There will be lots of rare events. I mean, you will not in every sample see all the categories. Anyway, it's a small sample. So here is some sort of rare sample event happening, and the same thing holds for 0.6 and even post-high. So there is this kind of right-hand tail for small values of it. What happened here now? So okay, here is k and 0.1, and then in fact the tail phenomenon is not as apparent as otherwise. We have also calculated the root mean square error of this based on these 1,000 sets of samples for these cases, and you see that initially for small values maximum likelihood estimates have much smaller root mean square error, but then when it increases they all converge to the same thing with the accuracy of 3 decimals. So this sort of like actually then verifies our theorem by simulations, and also sort of like provides a kind of proof of validity of the method of Boltz, right? Now here I have a couple of minutes left, and I got to the so namely this Jensen-Shannon divergence. It's in literature on statistical on machine learning. One refers to a paper by J. Lin in IEEE Information in 1991. But in fact, you find it in this book, Mathematical Taxonomy by Jardine and Simpson. It's called Information Radius of Order 1, and they're modeling dissimilarity in taxonomy. Don't ask me what dissimilarity is. I don't remember. I tried to find my notes when I was preparing. I didn't find my notes on dissimilarity. And so it is in fact, and they have there, for example, with this Jardine and Simpson proof is that if this Jensen-Shannon divergence equals the maximum value of its range, say binary entropy function at pi, then we can know if I take a sample of the distribution P, then I know for sure that it cannot be a sample of Q. Their supports are disjoint. And if I can decide without error that the sample of P cannot be a sample of Q, then the Jensen-Shannon divergence equals the maximum of its range. And then you can actually, then you can actually show that there's a connection to to Bayesian discrimination error. So when Jensen-Shannon divergence is sufficiently small, then actually you cannot, by say Bayes rule, discriminate between P and Q. But that's what we're actually trying to figure out. I mean, we're trying to find a model that is so good that you cannot discriminate between the real data and the simulated data. So therefore, this is the intuitive background, one of it in for Jensen-Shannon divergence. Then there's other person, Fleming Dupso, I can't pronounce it in a proper Danish manner, 1979, who defined this Jensen-Shannon divergence in a quite different manner. And he proved that, or he points out that, let's suppose that I have C. I have a Bernoulli random variable with parameter pi, and Q of x is probability of x given C2, P of x is probability of x given C1. Then this Jensen-Shannon divergence is actually nothing more than the Shannon information between C and X, when X is distributed as a mixture of P and Q, like that. So Dupso didn't use the word JSD or any notation, but he was talking about capacitory information in there. Now his interest was in information theory, whereas this Jordan and Simpson were doing mathematical taxonomy. And I hate to say it, but some 20 years ago, I read both Dupso and this Jordan and Simpson book, and didn't understand anything about it or what it was good for. I'm deeply embarrassed even today. So we are working on confidence intervals for this Jensen-Shannon divergence, and we are also working on model choice in likelihood-free inference using this JSD. Now, there obviously the solution might be to use some of the established criteria, and then simply instead of using the maximum likelihood, which is always had, you use the maximum or the minimum JSD. So thank you for the attention. That's it. 30 minutes. Yes.
Okay, thanks a lot for the very interesting talk. So now we have plenty of time for discussion. So if you have any questions, just raise your hand or write in the chat or open your microphone. And maybe in the meantime, when we are waiting for questions, so I wonder, do you have any plans or do you know if these developments could be incorporated in Boltz or to make a second version of Boltz?
I don't know. I'm not sure if who's got the copyright on Boltz. We confidence they might be there, but there's no plan of putting model choice in Boltz. That's what I'm sure. But I don't know. It is we haven't really discussed it, but obviously it might be a good idea to include these things there.
Okay. And I also have another question on the role of this pi. This was really interesting. So do you have any intuition on how the pi should be chosen? Or like, yeah, any ideas?
Yeah, I must say that I haven't really. I have tried to figure. I have sort of like strange inequalities that somehow would tend to say that the selection of pi equal to 1/2 is best in some sense. And the point is that if you look at this, if I now go back here a lot. The point is that if pi is too small, then these will also be small, and you don't have enough variation to make anything useful out of it. So the pi equal to 1/2 case is good because then you have the maximum range for your data to emerge, and then of course the pi equal to 1/2 has the advantage that if pi is equal to 1/2 and you take the square root of this as I mentioned, then it is a real metric, and that is useful actually. in analysis. But otherwise, I don't have any. I have tried to figure out some. It is of course also connected to this probability of error thing. But I don't have really any convincing intuition of how to choose pi. And anyway, in our simulations, the difference isn't that remarkable. But I can't give you a better answer than that. But pi equal to 1/2 has great advantages, as you see, in terms of what you then get.
Okay, very interesting. Thanks. So I see, Luigi, is there a question?
Yes. Yeah, thanks for actually a fantastic talk, really interesting. And yeah, actually, so the kind of work that you presented is, so you're kind of proposing a way to substitute the maximum likelihood, you said, with this minimum divergence, and you have several ways to do that. And is there any ways in which this could be extended to do Bayesian inference instead of getting a point estimate for the parameters, so you could get, say, a posterior or some approximate distribution?
Yeah, I think that's the. I think that is that's the. I don't have any mathematics connecting this to this particular stuff here to posterior to Bayesian inference really, but I think at least Elfi they do approximate Bayesian computation, but it's not like I had been thinking about that particular thing. This is the point estimate for sure, and then then we go to confidence intervals, which are very frequent in some strange terms. Though I feel Bayesian inference is the very thing to do, but somehow this has now turned into a confidence interval point estimate thing. Maybe it could be done. I'm not sure.
Thanks.
Okay, we still have plenty of time for discussion. Any other questions? Okay, so it seems that everything was very clear.
I can say one thing about this thing, yeah. Namely, there is this Igor Vaida, and I actually knew him, and I sort of like, we were on friendly terms, but and well, he passed away a few years ago, and he was a specialist on this phi divergence. But I never started talking to him about these things. I knew he was doing this thing, but somehow we always talked about all kinds of different things. I felt really strange now doing this thing, because now I suddenly learned what my friend had been doing, which I should have learned a long time ago. But things are strange. It is the same thing as with Jardine-Simpson and Topso. I had contact with it, but I never understood it before looking at this thing. I find it strange, or maybe you don't, but kind of coincidence of things. So that's all for me.
Okay, so in that case, I would like to thank the speaker and also thank the audience for the attention. And next week we will not have a coffee seminar, but then afterwards we try to continue. Okay, so have a nice week, everyone. Goodbye.
Bye.
Bye.
Joo, kiitoksia kovasti. Tämä oli erinomainen, tosi mielenkiintoinen.